Did you know one of the most famous dynamic programming questions is inspired by a staircase? Climbing stairs is a Pattern Mastery 100 classic and a favorite at Google, Microsoft, and Facebook. This deceptively simple problem shows if you truly understand recursion, DP, and how small problems build up to big solutions. Master it, and you'll unlock the core of Fibonacci-style thinking used everywhere in interviews. Let's break down the challenge. You're standing at the bottom of a staircase with n steps. Each time, you can climb either 1 or 2 steps. How many distinct ways can you reach the top? For example, to reach step 4, you could go 1, 1, 1, 1, or 1, 2, 1, or 2, 1, 1, or 2, 2, etc. Now let's assess our approach. A brute force way is to try every path recursively, exponential time. Instead, notice the pattern. To get to step n, you must have come from n1 or n2. So, the number of ways to reach step n is the sum of the ways to reach n1 and n2. This is classic dynamic programming, the Fibonacci sequence in disguise. We can use bottom-up DP or just 2 variables to keep it on time and o1 space. Let's structure our DP approach. If n is 0 or 1, return 1. Set 2 variables. First, ways to reach previous step. Second, ways to reach 2 steps before. For each step from 2 to n, update the number of ways. Current equals first plus second. Move the window forward. Set second equals first, first equals current. Return first. Let's try to implement it using solution 1. We start by defining a class named solution. This will hold our method for solving the classic climbing stairs problem, where each step count builds on the previous ones, much like the Fibonacci sequence. Here we create a memo map, short for memoization table. This map stores results we've already computed so we don't repeat expensive recursive calculations. Think of it like keeping a notebook of solved subproblems so we never solve the same puzzle twice. This defines our main method climb stairs, which takes an integer n, the number of stairs, and returns how many distinct ways there are to climb to the top. This handles the base cases. If n is 1, there is exactly 1 way to climb. If n is 2, there are exactly 2 ways to climb. So for these small values, we simply return n immediately, no recursion needed. This line checks whether we've already computed the number of ways to climb n steps. If the answer is already in the memo map, we return it instantly. This is what makes the algorithm efficient. We avoid recomputing results over and over. This is the recursive relation at the heart of the solution. To climb n steps, you can either take a single step from n, 1, or take a double step from n, 2. So the total number of ways to climb n stairs is the sum of the ways to climb n1 and n2. This creates a Fibonacci-like sequence. Once we compute the value for n, we store it in our memo table. This ensures that if the same value is needed again later, we can fetch it in constant time o1 instead of recomputing. We return the computed number of ways to climb n step. And that's how this algorithm works. It first sets up a memo table to store results, then uses a recursive Fibonacci-style formula to compute the number of ways to climb the stairs while caching previous values for fast lookup. Efficient, simple, and elegant. Solution 1. Test case 1. Let's test our function using this input. 2. Here, n represents the total number of stairs, and we want to know how many distinct ways someone can climb to the top if they can take either 1 or 2 steps at a time. For 2 stairs, the possible climbing paths are: take 1 step plus 1 step. Take a single 2-step move. That gives us 2 valid ways. Our recursive solution checks the base case n less than equals 2, returns n directly, and because memoization stores results for repeated calls, everything runs smoothly and efficiently. And that's exactly what our program outputs, 2. And the expected result also matches perfectly, 2, confirming that our memoized recursion behaves exactly as intended. So, our implementation is correct. The algorithm successfully identifies the number of ways to reach the top using memoized recursion, efficient and accurate. Now let's try another implement approach using solution 2. We begin by defining the solution class. This is where our dynamic programming version of the climbing stairs problem will live. This method, climb stairs, takes an integer n representing the number of steps and returns how many distinct ways you can climb to the top when you can take either 1 or 2 steps at a time. This line handles the simplest cases. If there's 1 step, there's exactly 1 way to climb it. If there are 2 steps, you can do 1 plus 1, or 2, so there are 2 ways. So for small values, we return n immediately. We create a dynamic programming array called dp with n+1 slots. dpi will store the number of ways to climb exactly I steps. Think of it like building a table where each entry depends on the 2 before it. These two values are our base cases. dp1 equals 1 way. dp2 equals 2 ways. These serve as the foundation for building all larger values. This loop fills in the rest of the table from step 3 up to step n. The rule is simple. To climb I steps, you either came from step I1 or step I2, so the number of ways to reach I is dpi 1 plus dpi 2. This creates the Fibonacci-like pattern behind this problem. Because this loop runs once for each value from 3 to n, the time complexity is O(n). After filling the dp table, the answer we want, the number of ways to climb n steps, is stored in dpn, so we return it. And that's how this algorithm works. It first sets up base cases for the smallest step counts, then builds upward using a dynamic programming recurrence that reuses previous results. Efficient, simple, and elegant. Solution 2. Test case 2. Let's test our function using this input, n equals 3. This value represents the total number of stairs, and our goal is to count how many distinct ways we can climb to the top when we can take either one step or 2 steps at a time. Here's why the solution works. The algorithm uses dynamic programming to build the answer step by step. For this input, to reach stair 1, there's only one way. To reach stair 2, there are 2 ways, either 2 single steps or 1 double step. To reach stair 3, we add the ways to reach stair 2 and stair 1. That gives us 2 plus 1 equals 3 total ways to reach the top. And that's exactly what our program outputs, 3. This matches the expected result and confirms that the logic behaves correctly for this test case. So, our implementation is correct. The algorithm successfully calculates the number of distinct ways to climb the stairs for this input, efficient, accurate, and reliable. Breakdown recap. We started by understanding that each step can be reached by taking either 1 or 2 steps from below. So, the problem is really about counting how many unique sequences of 1s and 2s can add up to reach the top, essentially, finding all possible combinations to climb n steps. Assess recap. We compared different approaches and noticed that brute force recursion tries every possible path, which grows exponentially. Instead, we discovered a pattern. The number of ways to reach step n is the sum of ways to reach steps n1 and n2, just like the Fibonacci sequence. Structure recap. We structured a simple dynamic programming solution by building from the ground up. Starting from the base cases, we iteratively calculated the total ways for each step. We started by understanding that each step can be reached by taking either 1 or 2 steps from below. Once we coded it up in LeetCode, the problem is really about counting how many unique sequences of 1s and 2s can add up to reach the top. Essentially, finding all possible combinations using LeetCode's built-in cases, confirming that every input passed successfully and the results matched our expectations. The key takeaway is that many complex problems simplify beautifully once you recognize the recurrence pattern. In this case, climbing stairs wasn't just about movement, it was about understanding how smaller subproblems build up to the complete solution.